let us continue to study time-dependent perturbation theory to compute the rate, transition rate from initial state to the final state. And we consider the simple situation. The initial state is just a single state among numerous states. And what I mean is we have state n, and n is allowed from 1 to infinity. And we assume that the initial state is just a pure state of I, initial I. And we are interested in the transition from state I to the final state, where final state is different from the initial state. Because initial state to the same state, it is not so much interesting because the rate is almost y. But the final state that is different from the initial state is initially 0 as a probability, but because of the perturbation dependent on perturbation contribution depending on time, it is possible to have non-zero probability to acquire the state that is different from the initial state. Okay, in the previous class, we have found that the change in time, depending on time, the change in the coefficient of Cm is satisfying this kind of equation, where n prime can be defined to be the time evolution of with respect to the unperturbed state, perturbed Hamiltonian H0 of the unperturbed state. All right. So we have all this element to be the n prime. And if we combine these two by moving this right hand side to the left hand side and factor this out, n prime out, then I have Cn time derivative plus I over h bar summed over state n, right?
Yes.
And because the n prime is different from n, that is the same as this, and actually this En can be replaced by H0. That is written like that. So I substitute this one to here, and this is a minus I over h bar H0t, and in here it is complex conjugate, so I have plus I over h bar H0t for the that is acting on state M. So matrix element from the state n prime to the m prime, sandwiching the potential, interaction potential V, can be written in such a way that n and m, and just substitute this factor here, that is exponential minus I h bar H0t, and it's complex conjugated to the left hand side. And this H0 reads the energy of the state n, this H0 reads the energy of the state n. So this is I h bar, okay, this is plus m and minus n. So if I use this one, this is En with negative sign, Em with a positive sign, plus minus minus. And matrix element of interaction potential V for the state n to m can be defined to be Vmn. And En minus Em divided by h bar can be defined to be omega nn. Like this. Okay. And the negative, I don't like this negative sign. To flip the sign, then this order of n and m can be flipped. Like that. Alright? So substituting this matrix element in here, I would get minus I over h bar, sum over n, matrix element of Vmn. This is prime, but the prime factor is factored out to the exponential I omega m and t. Alright? And Cn here, Cnt is in here. Let us solve this differential equation. This is a simultaneous system of equations, and we suppose the initial state at t goes to minus infinity is 1 only for the state I, that is the initial state, except that everything else is a state it's 0. So initial state is a pure state of I. Then suppose there is no interaction at all. Then there is no change in the state. So sure, there is some over factor of the exponential factor for the H0 evolution, but that is already included in the factor, that is already factored out. So actually, if there is no interaction at all, Ci infinity is exactly 1. And there is no phase factor at all. That phase factor is already factored out in here. And there is some correction of order V. We assume that V is very small in comparison with 1. So there is some correction factor. Alright? So let us call this is just equation number 1. And what about the state that is different from I? Then we can make use of this equation. If we integrate both sides, then here I have a Cn different from m. It may be the same as m, but if n is the same as m, then because m is different from I, everything else is 0. And the only surviving term is n equals I. Yes. So even though there is a sum over n, what I have to consider is just I. And V and I supply that. And Cit is just 1 in the negative infinity. And if we make use of this approximation, Ci is just 1. Neglecting higher order pieces. So if we substitute the fact that Ci equals just 1 from minus infinity to plus infinity, if m is different from I, is just 1. And it's just constant. And we can integrate this out. So let us integrate both sides with respect to I. If we integrate, initial value must be added to this definite integral, but initial value is 0 because n is different from I. So what I consider is just definite integral from minus infinity to infinity, and surviving piece is just for n equals I, and this factor is 1. Substituting those values in here, and Ci0 is the same as that, and this is just 1, and the final result is minus I over h bar, and there is no summation because I just consider state I, exponential omega mit vmi. Alright? And actually in general there is a time dependence appears in this vector field. Combining these two pieces, CF is approximated as in this way. In the case where F is equal to I, in the case F is not equal to I. In the case F equals I, this is not a good approximation, right? We just consider the leading order approximation. This is for the I state, and this is for the non-I state. Alright? The difference here is I just replace this M by final state F. Okay? Yes. Although it is written like that it is valid to order V, it is actually the leading order contribution. This is the leading order contribution for the initial state. This is the leading order contribution for the non-initial state, and remainder. Let us find the case if this time dependence is nothing. I mean, this VFI is just a constant. In that case, it is factored out of the integral. And this integral looks like a delta function. And this time integral, and you have delta, 2 pi delta omega Fi. Right? That means this delta function says omega Fi. Okay, argument is omega Fi means E energy of final state minus energy of the initial state. That means energy conservation. Initial state's energy must be the same as that of the final state of energy. So, this is the result. If the time dependence, there is no time dependence in the potential matrix element, then matrix element is just factored out of the integral. It is replaced by 2 pi delta function. Omega is actually the time, energy difference divided by h bar, and h bar is factored out of the delta function. It's upside down as h bar appears in the numerator. So 2 pi h bar VA5 delta EF minus EI is the value for this definite integral. Remember that the integral over time, in physics it is minus infinity to infinity, but actually the interaction is happening within a finite space, and before the interaction it is free particle, and after the interaction it is a free particle again. But the time, capital interaction time, capital P, is large enough to so that we can approximate that one to be plus infinity, minus infinity to plus infinity. So let us copy this result by replacing this one with the delta function. Then, still there's a minus I here, and time independent matrix element for the potential and energy conservation delta function appears. What about the probability of initial state making transition into a final state? That is just the square of this amplitude. If I square the amplitude, this is a complex number squared, so this guy multiplied by its complex conjugate. If I square this Fi, delta Fi is just identity. If I multiply two identity matrix, there's still identity matrix. So it should be, initial state must be the same as final state. So this square is the same as the single power. And next guy is this guy multiplied by delta function, Kronecker delta, and its complex conjugate. So I just copy this guy in here, minus 2 pi I delta Fi and delta EF minus EI, and add up its complex conjugate. There's a plus 2 pi I VFI, and so on. So its complex conjugate is minus VFI star, and I flip the sign in front of the imaginable I. But we assume that potential is real. If the potential is not real, what happens? Probability may change. If you assume that fact, the linear term vanishes, and I have the square piece.
리얼이 아니고 허미시안이 아니고.
Hermitian.
예.
Okay. Hermitian, then V, F, I, right. If it is not diagonal, it can be. If V dagger, where is it? V dagger is V, then V, F, I, star transpose is, if I simplify this, transpose V star IF, right?
Yes.
Equals VFI. right?
Yeah.
Then there is something wrong in here.
Yeah. But there are chronic delta Fi, so VII then so they satisfy the Hermitian function, then
Right,
they always
right.
satisfy.
If they are not diagonal, I can make use of this, but this chronicle delta gives that I must consider only diagonal term.
Yes.
So even though this is a square, so it is not summed over, so this is not VII. However, this can be written effectively delta Fi VII. I have to keep this delta Fi here minus a VII complex conjugate. So in that case, if I put f equals I, then these two values must be the same. Only for the diagonal component it is real. Alright? So it vanishes. And then Fi still Fi, right? Minus I plus I, so this is becoming positive, and 2 pi square, absolute value square of the potential matrix element, and delta square appears. And delta square is actually delta EF minus EI times this vector. Let me explain later over there. If I make use of this fact, what happens? I have time on the right hand side and single vector function. Let us divide both sides with the time capital T. Then probability divided by interaction time. That is probability per unit time divided to be transition rate. Transition rate is transition probability per unit time. Right?
Yes.
If the perturbation is turned on, the transition happens depending on time. If I turn off the perturbation, there's no transition at all. So transition is this means transition is proportional to the interaction time. All right. So I have 2 pi squared in the numerator. I have 2 pi in the denominator. So this 2 pi squared divided by 2 pi is 2 pi. And I have the numerator h bar in here. And this is just complex conjugate. This is a modulus squared. So VFI squared and single delta function. All right. So let us derive this fact that delta function, delta, if I have delta x squared, it is delta x times delta x, and delta x is actually minus infinity to infinity over 2 pi exponential I kx dk, something like that, right? I can rewrite this guy to be the limit capital T goes to 0 from minus half of t to half of t e to the I kx dk, right? And then I put 2 pi delta x, right? Alright. And because arbitrary function multiplied by delta function is delta of x, f of x integral is just f of 0, right? But that can be expressed as what? It is f0 integrate over just delta function. Right? So this means that if this is integrable, then the product function of delta and something else can be expressed as just f of 0. Let us make use of the fact f of 0. Limit t goes to 0, t goes to infinity.
Yeah. Infinity. 그거는
And exponential I0 dk. So this is just 1.
Yeah.
So integrating the, what's better?
t가 무한대로 가면 안 되고
Because this is omega. We could have omega. Then I would have omega t dt, omega t dt,
그 리미트가 없어요, 거기서.
omega.
왜냐면 사건이 마이너스 2분의 t부터
No problem.
네.
So this is 2 pi. I take the limit. T goes to infinity. 2 pi. T over 2 pi. Delta of x. Right? And actually this guy isn't going to the infinity. But what I want to compute is probability divided by time. So I will take the limit t goes to infinity after taking the ratio. Then it doesn't care. Yes?
저기 x가 다 오메가라서.
Omega.
좀 위에도 두 번째.
Where is it? Oh, omega. And if I rewrite this omega by delta omega is delta e over h bar, and it's h bar delta e. So this is h bar over 2 pi, right? Limit. Capital T goes to infinity. Delta E. Right?
예.
Delta no. Delta E and limit T goes to infinity. T.
그리고 바로 위에 줄이 dk 해도 상관없는데 그 로테이션을 따르자면 dt가 돼요. 네.
Alright?
예.
So we have shown that I assume that this is operator. There is something else before we take the limit t goes to infinity. If you take the limit t goes to infinity first and then take the ratio, you cannot find any answer. Okay? That's it.